Okay. Hi. So I'll be talking about material decarbonisation. We'll be looking at three main sort of route maps and then actually how that plots against where we should be. And then following that, we'll look at where the industry is going and also what you can do now. Just like to say that many of these slides are courtesy of Will, who is, I know, listening. So I hope I don't butcher them for you. But yeah, so let's get started. The supply chain expectations. We're going to look at three of the sort of key structural materials that we do use. So concrete and cement, and the roadmap produced by the MPA there. Structural steelwork decarbonisation roadmap produced by the BCSA, and then also the net zero roadmap produced by TDUK, which was released, I think, in January this year. Starting with concrete and exactly what's happening there. We've only included the emissions associated with production of concrete here. So that's why, if you're familiar with the roadmap, you might think that a couple of them are missing. So we've got indirect emissions from decarbonised electricity. So this is really, focusing on the fact that we are going to be decarbonising our grids. Also with transportation, we've got, we're not going to be producing combustion engines or selling new combustion engines from 2030 for cars and vans, and then 2040 for trucks, for diesel ones. So there are savings indicated there. There are also a focus on low carbon cements and concretes, which I think many of you might be more aware of because of all the, of all of the industry press around these sort of very interesting developments in that area. One is and then also in green there we've got fuel switching. So this is sort of moving away from fossil fuels, but also focusing on things like hydrogen production there. And then we also have a very large percentage dedicated to carbon capture, usage and storage, so CCUS, which I know that many of you on the call may be aware. We need to sort of really get behind UK investment in that, because at the moment I believe that only 0.12% of all emissions were actually captured by carbon capture and storage last in 2021. So a large upscaling of that is required if we're going to rely on it for that particular sort of way of decarbonising our materials. Also, there weren't necessarily sort of key dates associated with this. So these are a couple of assumed dates for when these savings will have been made. Moving on to steel. Again, savings that are within the BCSA document associated with sort of design efficiencies, etc., have been removed. We're just keeping it to emissions that are associated with production. So therefore, we should renormalize these CO2 reduction numbers associated with that. The first one, the largest one is emissions reductions based on the sort of direct steel making. So this is everything from sort of focusing on hydrogen production to changing fuel sources, those kinds of things. And again, with hydrogen, as with sort of carbon capture and storage, it really sort of relies on the fact that we're going to have to really invest heavily and upscale hydrogen if we're going to be sort of confident that it will provide us with the CO2 reductions that we need. Another point, again, with steel, as with the concrete, is reliance on the decarbonisation of our energy grid. And if we're sort of switching to more sort of electric led production processes, then we'll need to really sort of up that electricity and up our renewables. Again, as with concrete, there's an emphasis on carbon capture and storage. And then there are reductions due to steel transportation, fabrication, and erection as well. So this is, focusing on hybrid vehicles, machinery, as well as electric as well. Again, sort of assumed dates as to when this will be completed. Then finally to timber, even though it's actually quite a small percentage still of our construction and our emissions, it's always good to talk about it. Within the TDUK document, there is a graph here which has sort of projected reductions year on year as according to baseline. A lot of carbon emissions are actually associated to transportation for timber. And one of the reasons for this is because a lot of sort of forestry and forestry processes, we don't necessarily, as UK, TDUK, don't necessarily have control over in other countries. And so if other countries are not using sort of low carbon sources for their forestry, then this was considered outside the scope of this particular sort of transition graph. However, there is a breakdown in the document for terrestrial, so UK focused carbon emissions as of now, as a lot of moving around for sort of timber from forests to sawmills, etc., etc. A lot of these emissions are to do with fuel and transportation, but then there's also quite a lot of emissions associated with kiln drying of timber as well. So focusing on making those processes more efficient, and also sort of heat recovery and things as well. So, in summary, we have for concrete, as part of its roadmap, there is an emphasis on new cements, use of hydrogen, carbon capture, and then also sort of focusing on our improvements with the transportation and electricity grids. For steel, a similar picture. We've got more production efficiency, hydrogen, carbon capture, transport, and electrical grids. And then also for timber, there is a bit of a focus on hydrogen, but also electrified drying processes and transport and electricity grids there. I also wanted to include this slide with, I think it is UKGBC, where quite a few of these materials, and also other materials such as bricks, ceramics, plastics, vapor membranes, those kinds of things. Even by 2050, there is going to be a bit of a carbon intensity to those materials. And if we take the reductions due to carbon capture and storage with a pinch of salt, one could assume that we'll only really be achieving 40 to 60% of the reductions that we would hope with that as well. I think one of the key recommendations by the UK GBC is that if decarbonisation investments such as CCS are not planned for and delivered as projected, then other areas of the built environment will be required to deliver these reductions. So just want to state that. So by taking those kind of projected reductions and assumed projected reductions, and then putting it alongside the IPCC, which Will Arnold did a couple of months ago, as you can see, there's a bit of a discrepancy between those lines. It doesn't really even matter which material you're considering. There's a discrepancy. And so what we need to do is to close the gap. We can close the gap in two different ways. We can make our designs more efficient, and then we can also target the material production emissions as well. So how do we make our designs more efficient? We design more efficiently. And then also to reduce the material productions, we look into research and development there. So with R&D, we can sort of bring the lines closer to now, and then with more efficient design, we can just reduce the amount of carbon emissions we're emitting in the first place to hopefully keep it either to the IPCC 1.5 degree line or below. Right, so I'm not going to really focus on more efficient design because it has been focused on before, but it's always good to talk about the double triangle graph here. Please scan the QR code. I did redo it and I did check it, and it should hopefully take you to a longer document that talks more about the key tenet of use less stuff as structural engineers. So please, please, please read that if it's new to you. But what I will focus on now is actually the research and development portion of this. I wanted to talk about research and development through the kind of 4 different lenses of different innovations. This might be new to some of you, this might be old hat to some of you, but there's different ways of innovating, and there's different ways of doing research and development, and there's different ways of intervening with our designs. And one way of talking about sort of innovation is plotting technological newness, so from low to high, which potentially could also be called ease of implementation, because the construction industry isn't typically as agile as other industries. So typically, newer technologies are more difficult to get implemented in our projects, and older, more tried and tested ways are typically easier to get implemented. And then along the y-axis, we've got market impact. So we've got lower market impact, which might be, it doesn't bring about massive change in the market, or it doesn't bring about massive reductions in embodied carbon if only a couple of you do it. And so looking at these two axes, we can look at different innovations. We've got in the top left-hand corner there, architectural innovations. So these are significant improvements on a product that aim to sustain a position in an existing market. So this is where, sort of larger companies will be bringing out sort of low carbon versions of their materials, those kinds of things. Incremental innovation, so that's gradual and continuous improvement for existing products, keeping them ticking along, so that we're slowly but surely making our way there. Radical innovation, so maybe that's breakthrough technologies, and with those kinds of things, it might be the kinds of projects that the kinds of materials that need pilot projects to work within. And then there's disruptive. So this is a complete rethink of what we're trying to solve. Right, so hopefully I've given that an appropriate introduction, and now we're going to talk about it in terms of concrete. I'm also, this is very much a I don't know what the word is exactly, but this is very much like my first approach at looking at innovation for concrete materials in this way. So I'm very happy to be argued against. I'm very happy for this to be sort of tried and tested and changed around a lot. But this is kind of how I see all of the innovations within the concrete sort of sphere. Architectural innovations, we've got sort of cement replacements that are currently available to us within our codes. We've got different ways that we can actually approach total cementitious content reduction. So things such as admixtures, emphasizing slower strength gain, using 40 mil aggregate where possible as well, because that can have modest reductions on your total cementitious content. Doing enough GI so that you can be confident in what your DC class is for all the concrete that's in the ground. And then also setting CO2 limits within your specifications. They might not need to be like so stringent that it becomes a strain, but it should be just enough so that it's a stretch on business as usual. In terms of incremental, these can be things such as we've seen in the roadmaps earlier, sort of knowing that the decarbonisation of our energy grid and our processes are constantly improving anyway, those will have embodied carbon benefits there. In terms of radical innovations, I kind of saw these as cement replacements that are not currently in code, and I've got an extra slide on that next. And then with disruptive, it's sort of mainstream deployment of cement replacements within the radical window, or something completely disruptive, such as a global ban on the production of OPC. It's something that seems so out there that I think it should probably make quite a few people wince. It's that kind of innovation that fits into that window there. So this is the slide on sort of radical innovation for concrete, and this is courtesy of sort of flag waving from Sam. And this was a document that was, there's the link, or at least the citation below, pulled together by numerous people. I know that Expedition and Ramble have worked on this, as well as University of Bath, Cambridge, and a couple of others. But this is the commercial readiness of different cement production solutions, and those kind of radical innovations are sort of boxed out with the yellow there. So these will include things like biocements, AAMs, calcined clay, and those kinds of things as well. This document, I believe, is free to access, so please give it a read. I thought it was a fascinating document, fascinating piece of work. Moving on to steel. Again, sort of with the incremental innovation, we've got the decarbonisation of our grid. We've got sort of fuel replacements, moving to more renewables. We've got the incremental improvements in efficiencies, heat recovery, etc. In terms of the architectural innovations, it's things like signing up to Steel Zero commitments. It's things like putting a preference on open sections and S460 plus sort of steel strengths where possible. This is because those definitely with open sections, the way that they're produced, you're more likely to get a lower carbon steel than a plate that you can get in the UK, and also hollow sections. In terms of radical innovations, some of you may have heard of direct reduced iron, molten oxide electrolysis, closed loop blast furnace. So these are new ways of producing steelwork, which can have much lower embodied carbon than usual. So the usual sort of blast oxygen furnace route. And then disruptive might be something like, we have a 20 to 30% reused steelwork target for all new buildings. So that kind of thing, and emphasizing reused steelwork, because as we know, reused steelwork can typically have a much lower embodied carbon than new. Finally, with timber, again, as you can see, there's a bit of similarity between the incremental innovations here. We're waiting for the decarbonisation of our energy grid, focusing on renewables, etc., incremental improvements in efficiency, yada, yada, yada. And then for the architectural, it might be something like at least one timber or timber hybrid option in all of your stage 2 designs. It might be really strict specifications that no timber should be diverted to landfill or to burning in not a sort of heat capture kind of way, but also sort of maximizing reuse of OSB in small sections, the kinds of sort of lower quality timber, not the CLTs and the glulams, to make sure that they're not lost within the supply chain. In terms of radical innovations, this could be a sort of glue laminated bamboo and timber hybrids, which I've seen on my LinkedIn recently. Reused timber, akoya, which is like a pickled timber, which can have a much higher much better sort of durability in certain conditions compared to other timbers in those conditions. And also sort of looking at local sourced and coppiced feedstock timber as well. A lot of the time when you cut down a tree, it's the root bulb dies, and that sort of can potentially lead to methane production, etc. Whereas if you sort of treat timber more as a crop, where you can use coppiced timber, the root still stays alive, and you can grow more timber from that, and not have those timber carbon emissions associated with like the death of the root bulb and things like that. And then disruptive, might not be as disruptive as some people might think, but potentially minimum weight timber solutions, i.e., don't stop at CLT. CLT isn't the end goal. CLT is, okay, you've managed to get some timber into your project, but have you potentially looked at I-joist and LVL top and bottom skins? Like, have you looked at lower weights and pushing it further? Also disruptive could be diverting timber from short-term uses and using the whole tree. I know that Stora Enso has looked at, in the future, they will take a tree and they will have zero waste from that whatsoever. They will be able to use everything from that product. So that kind of thinking, I think, is more disruptive. Right. So in summary, need to close the gap. More efficient design, more R&D, but what can we do now? First one is use less stuff. Second one, I would say to you, is to have at least one timber or timber hybrid option in all of your stage 2 designs. Sign up for Concrete Zero. There are certain targets that you should meet for that in terms of embodied carbon requirements for your concrete specifications. Sign up for Steel Zero. That really sort of emphasizes the market demand for low carbon steelwork. Don't specify GGBS and scrap content. Apologies, I didn't actually go much more into that, but there is guidance on the iStruct websites following that, and I've got a QR code at the end. And keep talking and sharing as well. The more we talk about it, the more we share. The more we share where we've made a mistake or we've shared where something didn't quite work out, the sooner we can, work together and, save the planet. Cool. Thank you very much. And this is the iStruct sustainability resource map here. Thanks.